All right, good morning, everybody. We're going to pick up where we left off last time, thinking about the idea of a binary search tree and how it's organized, how it's manipulated, and so forth. We got a fair amount of practice last time with the idea of inserting values into a binary search tree. I'm going to go ahead and review that with you now. So let me go ahead and clear the screen from last time. And we're going to put together a simple binary search tree. So the insertion process then is, at some point we create a first node, okay? And that first node has whatever value we happen to be inserting. So let's say that that first node has a value of 12. Next, we're going to go ahead and insert another node. And the value we're going to insert is going to be the number 6. 6 being less than 12, we're going to go to the left and insert that node. The next value we'll insert will be 15. 15 being greater than 12, we're going to go to the right. Next, we'll insert 9. So when we insert a 9, we see that 9 is less than 12, so we go to the left. When we go to the left, we find that the value of that node is 6. So we go to the right, and we can insert the 9. Now we'll go ahead and insert 13. So we find that 13 is greater than 12, so we go to the right. 13 is less than 15, so we're going to go to the left. Now we'll insert 3. So 3 is less than 12, so we go to the left. 3 is also less than 6, so we go to the left, and finally, we are in a blank spot. And then we'll insert 18. So 18 is greater than 12, we go to the right. 18 is greater than 15, we go to the right, and we have some nice empty space right there. And so we've inserted 7 items into a binary search tree. If we were, and so we can look at this and we say it has a height of 2. So typically with binary search trees, we count the height in terms of how many hops do I have to take until I get to a leaf. A leaf is a tree node that has no children. A leaf is a tree node with no children. So how many hops do we need to get to a leaf? That's the tree height. And specifically, we try to think in terms of the maximum number of hops, right? So the minute I add one more node to this tree, the height's going to 4. Or to 3, yes. The height's going to 3. But if we get lucky and everything winds up in the right places, it'll stay at 3 for up to 8 additional nodes, as each of these 4 leaves acquires 2 children. That would give us 8 nodes. So that's what it looks like to have a binary search tree. Once we've got one in place, we can think about the search part of the name. So in particular, if I'm wondering, is the value 9 present, right? I ask the root, are you 9? And the root says, no, I am not 9. 9 is less than that, so we go to the left. And part of the beauty of this process is that we're able to completely ignore the right subtree because we know that it's maintained in this sorted ordering. So we go to the left. Am I 9? No. 9 is greater than 6, so we go to the right. Am I 9? Yes, I'm found. I'm there. I'm present. You could then imagine looking for something like 10, right? And it would take the same path. This isn't 10. We go to the left. 10's greater than this. We go to the right. 10's greater than 9, so we go to the right, and there's nothing there. So we would say it's absent. And this, by the way, is one of the main uses of the idea of a binary search tree. And we saw this also with the skip list. The way that I'm using it represents a set that is a collection of items where we're able to check for whether or not it's a member of that set. Much like a set in mathematical terms. And that often proves to be a very, very useful kind of data structure. Much as with a skip list, this could also be used to implement what is known as a map. And so a map is an association between keys and values, kind of like a dictionary in Python. So you can imagine just having the keys being how you organize the search tree, and then each key has associated with it some additional value that's been stored there. Sets and maps in general are just astonishingly useful, as we will be seeing in due time. So that's kind of a summary of what we've seen so far about the binary search tree. Any questions up to here? Okay. So one thing I've talked about is the idea that this keeps everything in a sorted order. But just kind of looking at it, how to get everything in perfect sorted order might not be altogether obvious. So let's start with a couple of basic ideas. Looking at this, how would I find the smallest value in the entire tree? Yeah, Sarah. Just go left and keep going left until there's no more left. And you have found the minimum. That is absolutely right. So I just want to know the minimum. Well, I'm going to ask my left child what the minimum is. I want to know the minimum. I ask my left child what the minimum is. I want to know the minimum. I ask my left child. Oh, wait, there is no left child. I am the minimum. I want you to see how well this works. I mean, this is sort of a nice, clear, obvious example. I'm going to add a 4 to this tree. So 4 is less than 12. 4 is less than 6. 4 is greater than 3. So it's going to be inserted right there. Note that what Sarah suggested still works. That is, you keep going left as far as possible. And even if that node has some right children, it's still the minimum because all of those children have to be greater in value than it. Otherwise, they wouldn't have been inserted there. So we can actually sketch this out as a simple algorithm, right? We could just say something like min of a tree looks something very much like this. If t has a left child, a chid, all right, child, return min of the left of t. Else return t's value. And voila, we have a beautiful algorithm to find the minimum value in a collection. We can also easily find the maximum. Any thoughts as to what a maximum function would look like?
It's just the opposite.
Okay, how so?
It's just right. You should go right.
That would be the right thing to do, definitely. So if you just go all the way to the right, you'll eventually find the maximum. So if you wanted to write an algorithm to calculate the maximum, it would look just like this algorithm, except that everywhere we have left, we would put in right. So this is something pretty interesting about a binary search tree. By virtue of its organization, it actually gives us both what a min heap can do and what a max heap can do. So in that sense, this might seem like a pretty powerful alternative to a heap. And in fact, it is. Especially if the tree is balanced. The min and max functions only need to do a number of operations equal to the height of the tree. which is going to be log base 2 of n. So it's very comparable to what a heap can do.
So for every, it could be for every, for height of, for every, I equals 0 then height, then height. Like you could check to do this and set another value and then have it return whatever that value is at the end.
I don't see what advantage that gets you over a straightforward recursive solution.
True, but
in fact, it's like actively more difficult because there's nothing to index, right? If you think about using a for loop tends to be pretty powerful when we've got a way of using that index value, like with an array. Here, not so much. In fact, you can think of something like a binary search tree as being like a linked list, but with 2 nexts, with 2 successors. So you've got 2 outgoing nodes instead of 1 outgoing node. You might wonder, well, why stop at 2? Couldn't you have 3 or 4 or 5? And the answer is, yeah, you can. And people do that. We'll come back to that theme maybe sometime next week. So that's min and max. So this is pretty handy, right? You've got this notion of an ordering, which lets you quickly find the minimum and maximum. But let's think about another level of it, which is how could we use this in general as a sorted kind of a container? So let's say I've got some value and I want to know something like next of that value. In other words, I want to be able to come into my tree. So I might want to be able to ask a question like, what is the next value in this tree after, say, 14? So I'm wondering, what's the thing after 14? Well, 14 is greater than 12, so I'm going to go to the right. 14 is less than 15, so I'm going to go to the left. 14 is greater than 13, so I want to go to the right. But I'm out of stuff, so now I need to backtrack, right? And now I'm kind of out of options. So I would think that 15 would be the thing after 14. Or I could even think in terms of something present in the tree. What's the value after 13? Well, I come in, 13 is greater than 12, 13 is less than 15. Oh, 13's right here. So I'm going to look to the right, and there's nothing there. And so I back up. And what was back up is that next value. We might have to back up fairly far. Like, what's the value after 10? So I come in here, 10 is less than 12, I go to the left. 10 is greater than 6, I go to the right. 10 is greater than 9, but 9 has no successor. So I actually have to backtrack all the way to the top, and I finally find my 12.
question.
Yeah.
Couldn't you create a function that checks that can return a right or left, the value of a right or left?
Yes. We
So
can do that.
if you were to use a call and then just call them is the if they're equal, they're like.
I mean, actually, I'm not sure what function you're describing. A function that gives the value of the right. Like, what's the value of the right of 12?
15.
The value of the right of 12 is 15.
Yeah, and then it will compare it. And then,
The value of the immediate right child.
yeah.
Well, you don't need a function for that. You can just look right at the node.
Okay.
The node's just sitting there. So you can always examine it. So The general concept here, though, right, is to find the next of a value, we look for that value, and we get as close as we can. We might hit it exactly. We might hit something that is immediately before it. That is, we find a leaf that's immediately before it. And then, kind of on the trip back upwards, is where we can get the value itself. But note that we can essentially read this right out of the tree, right? So let's think about building this as some kind of a recursive function, right? So under what circumstance do I keep going? Do I keep looking? Or alternatively, under what circumstance do I stop looking for my value? Of course, we need to reference having a tree as a parameter. Thoughts? If there's nothing after it, we're going to stop. So we might say either if tree.value is equal to my value, or tree has no right child. Now, what we're trying to do is figure out a value to return, right? And so we may actually have to pause here for a moment and think about what the basic recursive version looks like in order to figure out what we need to do here. So why don't we come down to the else? So otherwise, it has a right child. And so what we're going to do is we're going to call next on that value and the right child of that tree. Now, let's look back at our tree. What kind of information would we want in order to know what we need to return? So, let's say we're looking for the number 10. If I get down here, its value is less than 10. So that's not it. So I return some kind of placeholder, some kind of a null or something. I come back here, the value is less than 10. I have to, again, return some kind of placeholder. But I get up here, and the value 12 is greater than 10. And so this is a value I can return. Similarly, imagine the looking for the successor of 14 example. I come down here, there's nothing there. 13 is less than 14. I have to return some kind of a placeholder. I come back here, 14 is less than 15. Now I get to return 15, and I return 15 and so forth. So, if the tree value then is equal to the value, or the tree has no right child, we can return our placeholder. So some kind of a null value. And then let's just say v is equal to what we get in our recursive call. Now we have to have an if to determine what we're returning. So if tree.value is greater than v, we're going to return tree.value. Or wait a minute, let me fix that up. Whoops. If v is null, we'll return tree.value. Otherwise, we just return that null value. Or wait a minute. If v is null, we return tree.value. Otherwise, actually, I'm sorry, we return v itself. Because if v is not null, we need to propagate up the value that we got from the tree. So this is a pretty powerful idea. We're able to identify the idea that given some value, we can always find the thing after it. So if we've got a way to find the minimum value, and if we've got a way to find a successor, we can put these two together, and we can actually traverse the entire sequence of values in the tree. So this is valuable to know and to understand in the sense that we don't need to maintain very much state about the tree. Like, we don't even need to have a reference to a node in the tree. We just have to have the idea that here's the minimum, here's some value that I know to be, or here's a way to find the value after some value already in the tree. And I can actually get in sorted order all the values from the tree. And I can do that for any subsequence of values in the tree as well, just by starting at a particular value. I can ask the tree, give me all the values in this range from here to here. And I can do that. And I can do it in the other direction. Just as I can write a next along these lines, so too I could write a previous, a prev, along these lines. Now, if you happen to know that you want all the values from the tree, there's actually an even simpler way to do this, which is what I'm going to show you now. So conceptually, here's the idea. You dive all the way down in your tree to your minimum. Okay? So at any node you're at, you visit the left node until there's no more left node to visit. Now you do an operation on the value. You might print it, you might add it to a data structure, whatever. You know, like an array or a linked list or whatever. And then you go to the right. You perform your operation since there's no left child. There's no right child. And so now you backtrack. You perform your operation here. Then you go to the right, no left child, perform your operation, nothing to the right. You backtrack. You perform your operation. You go right, operate. No, actually you don't operate. You go left, perform your operation, no left, no right, backtrack, operation, right, and so forth. So that's an example of what's known as a tree traversal. And specifically, that's what's known as an in-order traversal. So let's imagine that you perform an in-order traversal in order to simply print all the values in the tree. It would basically look like this. If tree has a left, you're going to do in order on tree.left. Then you're going to print tree.value. And then if tree has a right, you're going to call in order on tree.right. And this is a complete algorithm for visiting all of the values in the tree in sorted order. And so this is called an in-order tree traversal. An in-order tree traversal. So this is a pretty powerful idea. The in-order tree traversal runs in linear time. That is, it does some operation once for every node in the tree. So once you've got it in a tree, you can actually examine everything in perfectly sorted order in linear time. Note the extremely clever use of recursion here. You can write this without recursion. Trust me, you don't want to. There are a couple of reasons for that. Now, when I say you don't want to, you should infer from that that I have in fact done so as a practical matter. So as a practical matter, what does it take to implement this without using recursion? Well, as I've said in the past, what recursion gives you is a free stack. You get to use the program call stack to store information. Now, if you don't have recursion, what is it that you're storing in the stack? Well, let's imagine you've gone all the way down to this poor node number 4 over here. You need to know, how do I ultimately get all the way back to 12? Well, if I'm not using recursion, I need to have a second parameter, which is a stack. And that stack is all of the ancestral nodes for that. And if you've got all those ancestral nodes, then to know where you need to go back to, you just pop the stack. So if I'm up here, when I go to the left, I push myself on the stack. So 12 is on the stack, then I push 6 on the stack, I push 3 on the stack, I get down to 4, I do my business, and then I pop 3 from the stack, and so forth, right? What the recursion does is, because in a recursive call, the entire function state has to be pushed on the program stack, we just use the program stack to remember where we were, which is a really powerful idea. It really makes life a lot simpler, a lot easier. And so that's a lot of why recursion is just so intrinsically beautiful. It is doing all of this data storage for you with less mental effort than otherwise would have been required. Furthermore, recursion is an elegant solution here because the data structure is itself recursive. That is, a tree is a data structure that has a value and 2 trees, the left tree and the right tree. Again, it's very similar to the linked list idea, where it was a recursive data structure that had a value and then a pointer to the next node. Here we've got a value and a pointer to the 2 next nodes. So that's the in-order traversal. There are other possible traversals. They aren't necessarily as useful as in-order, but they have their uses. So the other traversals are preorder and postorder. So what do I mean by these? With a preorder traversal, your print happens before you visit either of the children. In a postorder traversal, your print happens after you have visited the other children. Both have their uses. Let's envision what they look like, right? So let's say I do a preorder traversal of this tree. Well, I'm going to print 12, and then I'm going to go left. I'm going to print 6, and then go left. I'm going to print 3, and I'm going to go left and fail. And so then I'm going to go right, and I'm going to print 4. And now I run out of stuff here. Recursion ends, recursion ends, recursion ends. I'm going to print 9. Recursion ends, recursion ends. And then I'm going to print 15. And then I'll print 13 and 18. Now, on the face of it, this probably looks absolutely useless, which is fine. But now I'm going to show you a way to make this useful. Well, I think I'm going to. All right, here. So let's see. I'm trying to get myself enough space here. There we go. Let's just erase this. Let's say I print it like this. I print 12, and then I put in a new line character. Now I tab over, and I print 6. I put in a new line, I tab over, and I print 3. And then I put in a new line, tab over, and print 4. Now I back up, and then to where my 6 was, and then I tab over, and I print my 9. Now I back up to where my 12 was. I tab over. I print 15, and then 13, and 18. So with my preorder traversal, what I've done by clever use of new lines and tabs, so in order to do this right, I'd have to track my height, and then I put in another tabs equal to my height, right? I've created a textual representation of my binary search tree, where the depth of the node depends on how many tabs over I am. And I can use that to quickly visualize where the children are. So this is a pretty handy idea. And this is something that people have used for many, many years to help visualize a tree.
Wait, wouldn't post order be the opposite of this?
Yes, I wouldn't use post order to visualize a tree. Because if I did that...
No, it's just the opposite of the function. It's just,
yeah, pre-order is print at the start, post order is print at the end. Yeah.
Well, yeah, you print whatever you've got.
Yeah. So this is pretty handy, actually. This is the main way I've used pre-order personally. Post order is also useful. It takes maybe a bit more of a stretch to envision it. And in particular, I haven't found it useful so much in binary search trees as I have found it useful with the idea of a tree in general. The binary search tree is just one example of how we can structure data with a tree. Another type of data we structure with a tree is known as a parse tree. To think about that, imagine, did any of you in English classes ever have to do sentence diagramming? No? Sarah, why don't you talk a little bit about sentence diagramming involved? It was just horrible, okay. Anybody else remember sentence diagramming?
I don't think I've had it in a class like that yet.
So in a sentence diagram, you actually build a tree in this sense that shows the grammatical aspects of a sentence. So you would have something like, the boy runs fast, say. And so in your sentence diagram, you would say, well, I've got boy and runs as my subject and predicate, and the modifies boy, and fast is saying something about how the boy runs. Of course, for really good grammar, I guess we would say the boy runs quickly, making a nice proper adverb. But that's the idea of a sentence diagram, is you have kind of the core elements of the sentence near the root of the tree and ancillary modifying aspects further down the tree. Well, it turns out the way that compilers and interpreters work is they do the same thing with programming language code. And it turns out doing a post-order traversal of that tree is the most straightforward way for the compiler to generate code from the tree. And in my computing systems organization class that I'm teaching next semester, we learn all about that in tremendous detail. And we do a post-order traversal in that process. So the idea of tree traversal then turns out, in the sense of the binary search tree, gives us a basic intuition about how to retrieve this sorted information, but in a deeper sense tells us something fundamental about cool things we can do with a tree. So I'm actually going to end class early today. It is All Saints Day, and I'm going to Mass at 9 a.m., so I need a few minutes to bolt. So we will pick up on Monday with more details about binary search trees. There's a lot more to talk about.